Good morning, physics students. Here is your video going over the concept development practice page 6.2 about force and acceleration. So, again, we're going to use some of our equations. Primarily, we're going to use this idea that acceleration equals our net force divided by our mass. Okay, so remember that means that as our net force goes up, our acceleration goes up, and as our mass goes up, our acceleration should go down. Okay. So that's what we're going to be using. So number 1 says, Shelly the skater, total mass of 25 kilograms, is propelled by rocket power. Complete table 1, and we're neglecting any resistance. So we're kind of pretending that there's no resistance here. So one of the things here is as we do this, right, we see acceleration and force. To calculate acceleration, it's going to be the force divided by her mass. And the mass every time is 25 kilograms because it's not changing. Okay? And then so that's going to allow us to do the first two. So, okay, hopefully you can see that. Maybe we'll see how a light changes that. Well, if that makes it better or worse. Maybe a little bit better. So the first one, I want acceleration. So this is going to be A equals my force, which is 100 newtons, divided by my 25 kilograms. So 100 divided by 25 is 4, and we need units, meters per second squared. Okay. See if I can. Okay, so there's that. So now for the second one, my acceleration is my 200 newtons divided by my 25 kilograms. So 200 divided by 25 gives me 8. So my acceleration is 8 meters per second squared. Now, in this third one, they ask us to calculate force. So manipulating this equation, our force equals our mass times our acceleration. Okay? And our mass this time still is the 25 kilograms. My acceleration is 10 meters per second squared. Okay? So 25 times 10 is 250 newtons here. So B says complete table 2 for a constant 50 newton resistance. So remember, this is net force. So here, to figure out my net force, it's going to be force that they give me in my table minus my resistance. And this time my resistance every time is 50 newtons. So for this first acceleration here, my acceleration is going to be my 100 newtons minus 50 newtons divided still by her mass, which is 25 kilograms. So 100 minus 50 divided by 25 gives me an acceleration of 2 meters per second squared. So notice what we're seeing here is her acceleration up here with 100 newton force when there was no air resistance was 4 meters per second squared. We've decreased that because we have air resistance present. All right, and so for the second one, our acceleration is 200 newtons minus the 50 newtons divided by the 25 kilograms. So 200 minus 50 divided by 25 gives me an acceleration of 6 meters per second squared. And again, I'd really like you to have your work shown. So again, what we're seeing is air resistance is going to decrease our acceleration because our net force will be less as well. All right, looking at question number 2 here. Block A on a horizontal friction-free table is accelerated by a force from a string attached to block B. B falls vertically and drags A horizontally. Both blocks have the same mass m. Neglect the string's mass. So it says the mass of the system. So that means both of these, right? So the mass of the system is, of A and B, is 2m, because the mass of this block is m and the mass of this block is m. So the mass of both of them together is 2 times m. The force that accelerates this is the weight of, right? The only force that's causing the acceleration is the force of the mass of B. So that's just going to be the weight of B. The weight of B is, so again, weight equals our mass times our acceleration due to gravity. So if the mass of this object is B, and the acceleration due to gravity is g, the weight of B is mg. D. The acceleration is, okay? So it's talking about comparing it to free fall, right? G is the acceleration due to free fall. So the question here is, how does it compare to free fall? Well, it's going to be less than free fall because, okay, we have more mass, right? And when we look at our equation for acceleration up here, if I increase my mass, if my mass goes up, my acceleration goes down. And because the mass of my object is twice mass, it's going to be less than the acceleration due to gravity. So use A equals to show the acceleration of A plus B as a fraction. So again, our acceleration, okay, is our net force divided by our mass. So our net force here that's doing the acceleration is the mass of B times the acceleration due to gravity. The mass of the whole system is B plus A, so it's 2 times the mass. So now I have algebra to do, right? I have a mass on the top and a mass on the bottom, so they're going to cross out. And so I'm going to get 1/2 g. Or I could write this as g over 2. So down here it says, if B were allowed to fall by itself, not dragging A, then wouldn't its acceleration be g? Yes, because the force that accelerates it would only be acting on its own mass, not twice the mass. And it says to better understand this, consider 3 and 4 on the other side. So we're going to look at this a little bit more. So here's number 3. Suppose A is still a 1 kilogram block, but B is a low mass feather or coin. So what we're trying to do is we're trying to accelerate A with a feather. Compared to the acceleration of system 2 on the previous page, so compared to this one right here, okay, the acceleration of A and B here is going to be, is this little mass, right? Because now it's the mass of this feather, the weight of this feather trying to accelerate this. Is there going to be really any acceleration? No. So here, the acceleration is definitely going to be less. Okay, and it is pretty much going to be 0, right? You don't expect a feather to be able to accelerate something that has a mass of 1 kilogram. In this case, the acceleration of B is very constrained or restricted. Okay, so basically, this feather can't accelerate because it doesn't have enough mass. Number 4 says, suppose A is a feather or coin and B has the mass of 1 kilogram. So we've reversed it, right? Now we're saying we're going to pull this feather along here with the mass of this 1 kilogram block. The acceleration of A and B here is going to be close to g, right? Pretty much it's like it's not pulling anything here. In this case, the acceleration of B is practically that of free fall because there's no other mass here kind of slowing down the acceleration. Summarizing 2, 3, and 4, where the weight of one object causes the acceleration of two objects, we see the range of possible accelerations. Here, right, it was almost 0. Here it was free fall, so it's between 0 and g. A ball rolls down a uniform slope ramp. Acceleration is constant, and the reason it's constant is that it's a uniform slope ramp, so that makes the acceleration constant. If the ramp were steeper, the acceleration would be more. Because the ramp is steeper, that's going to increase the acceleration. Okay, compared to this one. It still will have a constant acceleration as it goes down the ramp, but the acceleration on a steeper ramp, if my ramp looked more like this, would be more. When the ball reaches the bottom and rolls along the smooth, level surface, it does not accelerate because there's no net force acting on it. Remember, gravity is acting on this ball on the ramp, and that is what's accelerating it, okay? But once we get on this level surface, gravity is acting on it, but it's not causing it to accelerate in a downward way. I hope that helps.